Hello students, good morning and welcome to another video lecture of physics. This is our fifth video lecture on moving charges and magnetism. Now in this video lecture we are going to discuss about motion in combined electric and magnetic field. Apart from that, in last video lecture we have discussed about motion of a charged particle moving in a uniform magnetic field. Then the magnetic force, right, due to that magnetic force it will perform a circular motion. Then we have derived the formula for radius, frequency, time of revolution, right? All those things we have discussed. The same thing which we have discussed in last video lecture, we are going to discuss in this video lecture, but for cyclotron, right? So first we'll start with motion in combined electric and magnetic field. Then we'll solve few examples based on the topic which we have discussed in last video lecture, and then we'll discuss about cyclotron. So the first topic for this video lecture is motion in combined electric and magnetic field. Motion in combined electric and magnetic field. Now look, we know that the force acting on a charged particle moving in uniform magnetic field the force acting on a charged particle moving in uniform magnetic field and electric field is given as, force acting on it is given as, like, of course this is the Lorentz force, there is Fe plus Fm, which is equal to Q into E vector plus V cross B vector, right? F equal to Q into E vector plus V cross B vector, right? This we have already discussed. This is the Lorentz force acting on a charged particle moving in a uniform magnetic as well as electric field. Now suppose the particle has charge Q. A particle is having charge Q, right? A particle having charge Q is moving along x-axis. It is moving along x-axis with velocity v, and we have assumed that electric field and magnetic field both are perpendicular to each other. So in this particular case, what we are going to consider, we will consider that electric field, magnetic field and velocity of the particle, all three are perpendicular to each other, right? So it is moving with velocity v in uniform electric field, which is along y-axis, and magnetic field which is along z-axis. So here we have assumed that particle is moving along x-axis, magnetic field is along z-axis, and electric field is along y-axis. So if we draw a xyz coordinate system, let us say this is x-axis, this is y, and this is our z-axis. So in this case, velocity is along x-axis, particle is moving along x-axis. So this is the direction of velocity. So you can say that velocity v is v I cap, because it is along x-axis. Electric field is along y-axis. Here electric field is along y-axis. So you can say that E vector is E j cap, right? And magnetic field is along z axis. So this is the direction of magnetic field. This is the direction of magnetic field, which is vector B, which is equal to B k cap. Okay, so what are the forces acting on it? The electrical force, electrostatic force, or the Coulombian force acting on the particle will be, the Coulombian force acting on the particle will be, we know that Fe, that is actually Q vector E, or you can say Q E j cap, which indicates that this electrical force will be along y direction. So here you can say that, so the electrical force acting on this charged particle will be in this direction. This is Fe, electrical force or electrostatic force or Coulombian force will be in upward direction, that is in the direction of electric field. Now the magnetic force acting on this particle will be, the magnetic force acting on this particle will be, the formula for magnetic force is Fm equal to Q into V cross B, right? So this is equal to Q into V, V is along x axis, so I cap cross B k cap. So this is QVB, I cross K, right? I cross K, anti-clockwise direction will be minus J. So this will be equal to QVB, minus of QVB or QVB in the direction of minus J cap, same thing we have written, right? So it means that the magnetic force acting on this charged particle will be in downward direction, negative z axis, negative y axis. This is the magnetic force which is equal to QVB, right, in magnitude. If you want to write in vector form, then Fm is actually minus QVB or QVB in the direction of minus J cap. This is the magnetic force acting on this charged particle. Clear? So clearly you can see that these two forces, that is electrical force and magnetic force, are in opposite direction. Electrical force and magnetic force are in opposite direction. Now suppose if the electrical force and magnetic force are equal, then what will happen? If electrical force and magnetic force are equal, then Fe plus Fm will become 0, which means that if these two forces, let us say this force Fm and Fe, that is QE and QVB, if these two forces are equal in magnitude, of course they are opposite in direction, right? So if both these forces are equal in magnitude, then if you add these two, resultant will be 0, right? So it means that if F is equal to 0, this implies that Fe will be equal to Fm. Both these forces must be equal in magnitude and opposite in direction. You can say that both these forces are equal in magnitude and opposite in direction, and then and hence F is 0. So you can say that here F is 0 if as Fe and Fm are in opposite direction, and if Fe is equal to Fm, then resultant force F will be 0. Means the charged particle will move without experiencing any kind of force. So for that case, for this case, Fe is actually QE and that is equal to QVB. So QQ will get cancelled out. So the velocity of charged particle will be equal to E by B. This will be the velocity of the charged particle moving in electric as well as magnetic field. Remember, in this case all three are perpendicular to each other. There is velocity, electric field and magnetic field, all three are perpendicular to each other, and in that case for the given condition whatever we have discussed, V will be equal to E by B. And this is the most important point, because look, if this is the velocity, if you select electric field and magnetic field in such a way, for the given condition, if we select electric field and magnetic field in such a way that these two forces, that is electrical force and magnetic force, are equal, then the velocity which is equal to E by B, that is the particle with velocity E by B, will move undeflected. Means the particle will not experience any kind of force because net force is zero and it will travel without getting deflected, right? So for this condition, the particle moving in electric field and magnetic field will continue to move in the same direction without getting deflected. And hence this method can be employed, or you can use this method for selecting a particular particle with a particular speed out of the beam of particles moving with different speed. Suppose we have a beam of particles, right? We are getting large number of particles moving with different speeds. In that case, if you arrange, suppose particle is moving in this direction, so if we keep two plates of the capacitors, right, one is positive and negative here, then this will be the direction of uniform electric field, right? And if you keep a north-south bar magnet over here, north pole of a bar magnet and here south pole, then we will have a uniform magnetic field towards you. So this will be the direction of uniform magnetic field and this is the direction of uniform electric field. And those charges which are moving with different speed are allowed to move along x-axis, right? So all three are perpendicular to each other. Now in this case, only those charges which have velocity v, which is equal to E by B, will pass through it without getting deflected. And for the rest of the particles, they will get deflected, means they will start performing circular motion, that helical motion, right? So you'll get a particular charge. You can select a particular charge moving with a particular speed. Remember, this indicates that V is equal to E by B, which simply means that it is independent of charge and its mass. Whatever may be the value of the charge and whatever may be its mass, it will move undeflected, or it will not get deflected if the value of E by B, right, E by B is equal to its velocity, right? So that particle is moving with velocity E by B, then you will get it will move in such a way that it will not get deflected. Clear? So we can select a particular particle with a particular speed out of number of particles moving in a particular direction, right, by selecting the value of E and B, and that is why it is known as velocity selector. The same concept was employed or used by J.J. Thomson in the experiment which he performed in 1897 AD, right? And through that experiment, he found the value of E by M, right? So the same method was used by him to find the ratio of charge to mass of an electron. And the same concept is of course used for mass spectrometer, which you have learned in chapter atoms or nucleus, right? There you might have come across mass spectrometer, which is basically used to find the ratio of E by M. Clear? So do one thing, pause this video and copy this first. Now in last video lecture we have discussed that when a charged particle move in a uniform magnetic field perpendicular to it, then it will always follow a circular path, right? Suppose if magnetic field is perpendicular to the plane of the board and it is entering inside, and we have a positive charged particle moving in this uniform magnetic field, then the magnetic force acting on it will be towards the center of a circle, or you can say that it will provide the necessary centripetal force. So the charged particle will perform a circular motion, right? If here is the charged particle moving with velocity v, then it will experience a force in this direction, right? So the necessary centripetal force is provided by the magnetic force. So mv square by r will be equal to qvb sin 90, because magnetic field and velocity both are perpendicular to each other. So if you cancel v, then radius of the circular path will be mv by qb. This we have already derived. Radius of the circular path is mv by qb. Also from this equation, let us say r equal to m. What is velocity? Omega r. V is equal to r omega, right? qb. So 1r will get cancelled out. So omega will be equal to qb by m, right? But actually omega is 2 pi f and that is equal to qb by m. So this implies that frequency will be equal to qb over 2 pi m. This is the another important formula which you have to remember, right? Based on this, we have one example, that is solved example 4.3. Example 4.3. What is the radius of the path of an electron? Mass of electron is given as 9 into 10 to the power minus 31 kg, not 9.1, right? And charge is given as 1.6 into 10 to the power minus 19 coulomb. You can write this is equal to E, that is 1.6 into 10 to the power minus 19 coulomb. Moving at a speed of 3 into 10 to the power 7 meter per second, the speed of electron in a magnetic field is given as 3 into 10 to the power 7 meter per second. In a magnetic field of 6 into 10 to the power minus 4 Tesla, the magnetic field in which this electron is moving is 6 into 10 to the power minus 4 Tesla. What is the radius actually? So we have to find the radius. Look, if you remember this equation, you can directly write, or you can say that when a charged particle is moving in a uniform magnetic field, the necessary centripetal force is provided by the magnetic force, and you can derive like this. So let us say when a charged particle is moving in uniform magnetic field, the necessary centripetal force is provided by the magnetic force acting on it. Magnetic force acting on it, that is centripetal force equal to magnetic force. What we have done here, same thing. So therefore centripetal force, actually directly we'll write mv square by r. Mv square by r will be equal to qvb sine 90, because it is perpendicular to magnetic field. So V will get cancelled out. So you can write R will be equal to mv by qb sine 90 is 1. So this is the formula for radius. So therefore R will be equal to, mass is given as 9 into 10 to the power minus 31, velocity is 3 into 10 to the power 7, charge of electron is 1.6 into 10 to the power minus 19, and magnetic field B is given as 6 into 10 to the power minus 4. 6 into 10 to the power minus 4. So if you calculate this thing, nine into 3 divided by 1.6 divided by 9 into 3 divided by 1.6 divided by 6 will give you 2.8125 into 10 to the power. Look, minus 19 minus 4 is minus 23. Minus 23 will move up. So plus 23. Plus 23 plus 7 is 30. 30 minus 31 is minus 1. So you can write this as 28.125 into 10 to the power minus 2 meter, or 28.125 centimeter. This will be the radius of that circular path. Clear? Next, what is its frequency? We have to find frequency also. This is the first case. In second case, we have to find frequency. So if you want, you can derive, or you can directly write. Let us derive this thing. Do one thing. We can derive like, let this be equation number 1. From equation 1, R, which is equal to m upon qb, and v is equal to r omega, because v is equal to r omega. So r will get cancelled out. So therefore qb will be equal to m into omega is 2 pi f, because omega is equal to 2 pi f, right? So therefore frequency f will be equal to qb over 2 pi m. QB over 2 pi m, what we have derived over here, right? So therefore F will be equal to Q is 1.6 into 10 to the power minus 19, B is 6 into 10 to the power minus 4, QB over 2 into pi is 3.14 into M is 9 into 10 to the power minus 31. So 1.6 into 6 divided by 2 divided by 3.14 divided by 9 will give you 0.16985 into 10 to the power. Again, look, minus 19 minus 4 is minus 23 plus 31 is 8, 10 to the power 8, or you can write 1.6985 into 10 to the power 7 hertz. If you want, you can round up 1.7 into 10 to the power 7 hertz. This will be its frequency. Third thing, we have to also calculate its energy in keV. keV means kilo electron volt. We have to find energy in kilo electron volt. So kinetic energy is given as half mv square. We know that kinetic energy of a charged particle moving with velocity v is half mv square. So therefore K will be equal to half into m is 9 into 10 to the power minus 31 into, directly we will write v square, or let me write 3 into 10 to the power 7 whole square. 9 divided by 2 is 4.5 into 10 to the power minus 31 into 3 square is 9 and 7 2s are 14. So 4.5 into 9, 4.5 into 9 will give you 40.5 into 10 to the power minus 31 plus 14 is minus 17. This is in joule, but we want energy in keV. It is given 1 EV is 1.6 into 10 to the power minus 19 joule. So 1 joule will be equal to 1 divided by this. So this many joule. So therefore you can directly write K is equal to 40.5 into 10 to the power minus 17 joule. Right, and 1 joule is 1 divided by 1.6 into 10 to the power minus 19. Take this on other side. So 1 divided by 1.6 into 10 to the power minus 19 will be equal to EV. Right. So to convert this into EV, we have to divide by 1.6 into 10 to the power minus 19 in EV. So 40.5 divided by 1.6 will give you 25.3125 into 10 to the power. Minus 19 will move up. So plus 19 minus 17 is 2. We want in kilo electron volt. So 2.53 into 10 to the power 3 EV, or you can write this as 2.53 kilo electron volt. keV is kilo electron volt. Clear? Pause this video and copy this. Now we do have one more example which is exactly similar to this, right? That is solved example 4.4. We do have two more example in exercise, unsolved example 4.11 and 12, I think, right? So all those examples are based on cyclotron, working of cyclotron which is left. But as we have derived formula for frequency, look, whatever frequency we have derived here is actually the frequency of cyclotron. Right. So same formula can be used for solving examples. So we'll solve example 4.4, and in next video lecture we'll discuss about cyclotron and we'll solve the two remaining unsolved examples from this chapter based on cyclotron. Right. So example 4.4. A cyclotron's oscillator frequency is 10 megahertz. Frequency, operating frequency you can call 10 megahertz. So that is 10 into 10 to the power 6 hertz, or you can say that 10 to the power 7 hertz. This is the frequency, operating frequency. What should be the magnetic field for the accelerating protons? In order to accelerate proton, what must be the magnetic field? So first thing, we have to find magnetic field for proton, right? If the radius of the disc is 60 centimeter, radius of the disc is given as 60 centimeter, that is 0.6 meter. What is the kinetic energy in MeV of the proton beam produced by the accelerator? We have to find the kinetic energy. In MeV, million electron volt. This is not mega electron volt, it is known as million electron volt. Constant values are given. Charge of proton, which is E, is given as 1.6 into 10 to the power minus 19 coulomb. Mass of proton is given as 1.67 into 10 to the power minus 27 kg. And 1 MeV, 1 million electron volt, is 1.6 into 10 to the power minus 13 joule. Remember, these three datas or these three value might not be given in your exam, Q, MP and MeV. Right. So let us solve this thing. We know that the frequency of cyclotron given as, the frequency of cyclotron is given as F equal to, just now only we have derived QB by 2 pi m, F equal to QB upon 2 pi m. So the frequency is QB over 2 pi m. So this implies that B will be equal to 2 pi Fm over Q. Look, if you want, you can derive this formula which we have derived in previous example, that is example 4.3. Here we have taken, we have written directly, right? In that example also you can write directly. You must check the marks of a given example, right? Suppose if this is asked for 3 marks, then of course we will derive this formula. And if it is asked for 2 marks, you can directly write this formula, right? So this is equal to, or B is equal to 2 into 3.14 into frequency is 10 to the power 7. Mass of proton is 1.67 into 10 to the power minus 27 kg and charge is 1.6 into 10 to the power minus 19. So 2 into 3.14, 2 into 3.14 into 1.67 will give you 10.4876 divided by 1.6 will give you 6.55475 into 10 to the power. Minus 19 will move up, plus 19. Plus 19 plus 7 is 26. Right? Plus 26 minus 27 is minus 1. So you can write this as 0.655475 Tesla. This will be the magnetic field, operating magnetic field or required magnetic field. Second thing, we have to find kinetic energy. Now formula for kinetic energy is half mv square, which means that we should know velocity. Now velocity can be calculated in many different ways. Directly we can use the formula. We know that the radius of circular path is given as r equal to mv by qb. So this implies that v, velocity, will be equal to qbr over m. qbr over m. Now if you want, you can simplify over here. We will simplify when we will calculate this, right? For final calculation. Now kinetic energy is given as half mv square. So that is half m into v square is q square, b square, r square over m square. So 1m will get cancelled out. So that is half into q 1.6 into 10 to the power minus 19 whole square into b 0.655475 whole square into Our radius is given as 0.6 meter. So 0.6 whole square over mass of proton is 1.67 into 10 to the power minus 27. So if you simplify this, 1.6 into 1.6 into 0.655475 into 0.655475 into 0.6 into 0.6 divide by 2, this 2, right, divide by 1.67 will give you 0. This will be equal to 0.11855 and so on into 10 to the power. Now look, minus 19 into 2 is minus 38 and this 27 will move up. So plus 27 will give you 11, minus 11. So into 10 to the power minus 11 joule, right? This is in joule, but we want in MeV. So this is equal to 0.11855 into 10 to the power minus 11 divided by 1.6 into 10 to the power minus 13. So this will be equal to 0.11855 divided by 1.6 will give you 0.07409 and so on. Now into 10 to the power minus 11 plus 13. So 10 to the power 2. So you can write 7.409 MeV. 10 to the power 2 is 100. So if you multiply by 100, 7.409 MeV. This will be the kinetic energy. Clear? So look, in this video lecture we were supposed to discuss about cyclotron, but I think almost time is over. So we will discuss cyclotron in our next video lecture. Remember, in cyclotron again we have to derive the formula for the frequency, right? What we have derived here. So that formula will derive how cyclotron works and what are its limitations. That we will discuss in our next video lecture. Clear? Thank you.